CAT stands for Customer Advisory Team, so we still go by SQL CAT. But as you can see, in terms of the technologies that we look at, they're much broader than just the SQL ecosystem. So we're now kind of going by data CAT. We are part of the Microsoft Azure engineering organization. And in terms of our focus area, our primary goal is to help customers be successful with Azure. And in doing that, we try and go deep with those customers. So if you look at some of our sample recent engagements, be it lab engagements on new technology like SQL Server 2019, or working with early adopters of SQL Database Managed Instance, or developing architectures with customers and validating those architectures on SQL DW. Those are the type of engagements that we do. And in going deep with those customers, we get to learn a lot. We get to help them, we get to learn a lot. And so a second goal of ours, and a third goal is to deliver that feedback, that customer feedback and those learnings back to engineering to ultimately improve the platform. And then also to share those learnings with the community and you through sessions like this. So a quick agenda. We're going to do a quick overview or review of SQL DW Gen 2 architecture. Our recent engagements and the things that we're focusing on here, while some may be applicable to Gen 1, all our recent engagements have been on Gen 2 of SQL DW. So that's what we're going to primarily focus on and talk about today. We'll talk about some common patterns and architectures for SQL DW. In essence, reference architectures for a number of the customers that we've worked with. Then we'll talk about some schema design considerations, data loading considerations, query performance and optimization. And then we're going to talk about analysis services observations. This is in particular in the context of pulling data from SQL DW to analysis services. So it's not deep on analysis services per se, but just in terms of optimizations around that. And so a question for the audience, and then probably one comment. How many people either have deployed SQL DW or are working on a project with SQL DW? Okay, that's awesome. That's very good. Gen 2? Okay, cool. All right, and then we do have a lot of slides to go through. We may be able, obviously we can take questions way back there, but we'll probably defer most of the questions to the end. And then we're happy to stay around as long as possible to answer any questions that you may have. So I'll also note again on this agenda, if somebody doesn't feel like it may be applicable to them, we won't be hurt if you happen to leave, but we'd love for you to stay. All right, so with that, let me turn over John to you.
Sure. Hi there. So again, I'm going to go a real quick overview of the SQL Data Warehouse, given that the majority of people out there are already familiar with. So bottom line is that SQL Data Warehouse is Microsoft Azure MPP, distributed system, database system. And as you can see from the screen right there, you got the control node, which is basically the brainchild. And so what it does is it has an engine which is orchestrate, and it would parse and distribute all the query plan to each one of these compute nodes right here. Note that each one of these nodes, we have about 60 databases, or we call it distribution. So all the data, the fact data, are being basically distributed out into 60 pieces into its own databases, right? And then as the query is being submitted, the control nodes would basically orchestrate and as it parse and then submit the queries, the SQL plan, we call it the distributed SQL plan, among all the compute nodes. And the compute node goes out and carve its own slice of data, does its own work. And if the data, the result set is there's no aggregation, it can stream directly to the client. If there's an aggregation or any type of final aggregation that needs to be done, it goes back to the control node and move back to the queries. Again, the big thing with Gen 2 that we have is obviously the separation of compute and storage. It gives you the capability to scale at in as little as a few minutes, so you can basically scale the data to almost thousands of cores that will become available right now, because you can see right there, we have the lowest we recently released is the DW500. That's the lowest that you can have. And you can go up to 30,000, which literally means thousands of virtual cores out there. And so I think that's, this is probably like the largest resources out there that you can have on MPP right now on Azure. The only difference is that the taking advantage of the multi-tier storage, specifically caching. So we leverages obviously the cold data is going to sit out there in the remote storage, and then then you have the tier of the high performance NVMe SSD and also memory. So by leveraging all this caching right there, we see really, really great performance compared to our Gen 1 architecture. And this is basically just showing you the caching algorithm. Mike, you want to talk about concurrency? Is it? Yeah. Oh, what am I talking about? Okay. All right, so one of the things that, as you know, that any system, there's always going to be some resources that you can allocate, and you want to make sure that you manage that resources so everybody have a piece of the pie. In a typical enterprise, data warehouse, you're going to have lots of data loading. You're going to have user querying the data. You're going to have, SSAS processing, and among other things. So what we do is that we control that resources through the mean of what we call resource class. Each one's resource class right now is we're controlling the certain amount of memory, and we limit certain amount of concurrency so you can have the resources needed. And I'm not sure if you got a chance to attend the SQL Data Warehouse. What's new? Obviously, one of the things that we're looking for is resource governance, controlling the DWUs, giving prioritization, and resource isolation that's coming down the line. But right now, what you have is basically we can control their memory and also limit the concurrency of the queries. So dynamic is what we started out, that's a legacy. And in the beginning, it's just basically allocating a certain percentage of the total memory of the node to each one of these resource class. So originally, we had 5 resource classes out there. We allocate with 3% of memory. Whether you get DW 1,000 or 6,000, you would take all the memory and allocate that. So that's why we call it dynamic resource class. Memory grows. And the usage of that is obviously, if your data actually, when you carve off the data, whether you do scanning or shuffle move, if you need that's the resource to go after, then you would use the dynamic. But as we go forward, the way that we help resolve the high concurrency is that we create the static resource classes, which basically assign a fixed amount of memory to each one of the resource classes. And this is the way, and then it ranges from 10 to 80. What that does is that it gives you more granular level over the concurrency and the resources that you originally didn't have with the dynamic. So as you see from the chart right here, you can start out, depending on the resources, right? From the DW 1000, the high is 32. But if you want to leverage the full 128 concurrency, you want to scale out to DW 6000. That's where you get the 128 concurrency that you're looking for. Whereas, as you can see, the dynamic resource class, it flattened out at 32 all across, regardless of the DW that you use this. Okay? So Mike's going to talk a little bit about the implementation patterns from our customers.
Okay, thanks, John. So this next section is kind of just a little bit about planning and implementation. So we'll show kind of the reference architecture in terms of a lot of the customer solutions that we've worked with them on. Again, most of these customers and most of the workloads that we've got are very high concurrency, high performance, kind of large analytics workloads. Lots of end consumers that are trying to query that data in fairly significant concurrent load scenarios. So having said that, I just want to set a little bit of context for the people that are obviously on DW. That's great, but they probably have some familiarity with this. But This is really around just evaluating the workload fit for SQL DW, right? So SQL DW is a great MPP solution. You can take advantage of the scale-out compute cores, but not all workloads can ultimately take advantage of that. So a couple of the considerations here. First is it's really, if you're looking at SQL DW, it's not really just a function of size. So I wouldn't necessarily say, hey, if I have a couple of terabyte size database, let's go into SQL DW, right? It's really about the workload. It's an analytics workload. If it's optimized to process and analyze kind of large, complex queries. And then typical batch workloads are ideal, right? And just extremely large amounts of data very quickly in utilizing all of those compute nodes. So the counter to this would be OLTP workload, right? Singleton inserts or singleton DML could be very chatty on the network. It can't really take advantage of all that compute that you have there. So that's not a typical workload that will work well with SQL DW. A couple other considerations, again, with SQL DW, as John mentioned, the concurrency, 128 on the high end. Lower SKUs will typically have less, or will have less. And then query latency SLAs. So this is a typical scenario that we get with a number of customers, again, that are pushing high concurrency workloads, a number of queries, and a number of scenarios where they'll have dashboard type queries where the SLAs may be, say, 3 to 5 seconds for the execution of that particular query. So we'll typically use a caching layer in front of SQL DW to handle this. So to a number, quick question?
What's the smallest size you guys recommend for SQL DW?
The question is, what's the smallest size we would recommend for SQL DW?
So again,
So the question is, just really quickly, and then question is, it was initially on size, but it's really considerations between, say, SQL DB and SQL DW.
so I guess the quick question is, are you experiencing any pain points right now with your current on-prem system, right? Whether you're coming from on-prem. So the point is that the scale out, well, it's not necessarily storage anymore, right? Because we have hyperscale that can go up to 100 terabyte recently, right? We just recently announced SQL DB with the column store can handle much more than a few terabyte. The point is that in addition to the storage capacity that you may have limit, it's all about resources. Is your system or even any of the SQL instance that's available right now, is that high enough? Is the scale up, exceeded your limit? Because a lot of time we see some workload that are resource intensive, but they may processing a very small amount of data, but because they require that scale out compute power. And so I think that's probably word that you need to do. So the best thing is that take a look at the resource utilization that you have, whether it's memory or CPU or even I/O. If you actually exceeded that on your environment, then you would use scale out. That would be the way to go. Did that answer your question? Okay.
Yeah, there's probably a few other nuances that we can probably talk about afterwards. So this is the kind of, this slide may look familiar to a number of people if you've seen our modern data warehouse architecture slide. Again, I'll step through it relatively quickly, but this is kind of the common reference architecture that we've worked on with a number of the customers that have kind of come to us in implementing SQL DW. So just at a high level, if we kind of go from left to right, typical scenario is a large number of data sources. In terms of that data in those data sources, you may have structured, unstructured, or semi-structured data. You need a place to land that, and typically you're looking for some orchestration tooling to move that data from wherever it is into, in this case, Azure storage, which will typically be your data lake. So we've typically seen Azure Data Factory and utilized that as a tool to do that orchestration, right? Then once you're in Azure storage, again, this could be blob, ultimately, in most cases should be ADLS Gen 2. The decision point is what type of data you actually have there, right? So if it's structured data, you could probably just use Polybase to go directly ingest it into SQL DW. If it's semi-structured data or some kind of data source that, Polybase doesn't natively support and ingesting into SQL DW, then you may need to do some transform on top of that. So Spark can help out with that. Azure Databricks is been a very popular solution to do that transformation in our particular case, and then it has native connectors, obviously, into SQL DW. So on the kind of client side, again, for concurrency and the low latency SLAs, we've seen Azure Analysis Services, and then ultimately you can have Power BI. Of course, with a number of customers, and John will talk about this a little bit more in terms of the analysis services considerations. Some customers, data models just don't fit into analysis services, so Azure Analysis Services, so we've used analysis services in a VM there, and then other typical patterns is not everybody necessarily has everything in Power BI. So this architecture certainly works with other dashboards and client tools. So Alexei, do you want to talk a little bit more about it?
Yeah, so this is kind of blueprint what, as we said, we not only see on multiple decks, but we really use in customer scenarios. And one of the questions what I found interesting, which comes quite often and from the customers, like we see the cool kit and the block, Azure Databricks, for example, or some other technology, and apparently it should replace relational engine, whether it is not bad idea to replace SQL data warehouse and go away from traditional relational type of querying and do it in like super fancy and modern NoSQL way. Or we also introduced a couple of functionalities, like, for example, Power BI now can read directly data from blob storage. Then why not to remove all this overhead and go straight to the blob and read the data? What the reality shows is each of the tools has own limitations, right? So Power BI, if you go access blob storage directly, you cannot do complex join queries on top of this, right? So on the blob, you first need to read data, and then you would do query then in Power BI level. And reading data, so Azure Storage has like certain characteristics, right? And you cannot jump over those limits, so it will your speed of loading data in Power BI engine will be limited by the speed of the Azure blob. Then Databricks is also a cool thing, but for complex joins, like for example, what often happens, like year-over-year calculation, Databricks is not good for. Databricks, I mean Spark, let's not talk Databricks because it's like one of the implementations of Spark, right? It's really good for large and massive transformations. So if you remember old days when we were talking about data warehousing in general, you would usually have stages like data source, staging area, then data warehouse, and data marts. In the modern world, staging and the transformations happening in NoSQL level, SQL data warehouse is extremely good in doing the role of the data mart. So this is where you can do relatively, and all BI is still benefiting from, like it runs way, way faster on traditional quote unquote relational engines rather than those NoSQL engines. Like if the query needs to do fast lookup, often a relational engine does it way faster than any of the NoSQL machines. So therefore, like yes, if your workload fits certain requirements, like all what you do, you read all the data in the Power BI and then you do slice and dice. There, definitely you can remove certain layers. But often the life and scenarios are way more complex. People may have some like commodity applications or dependencies which require a relational engine being there. Therefore, we prefer to stick to this architecture, to this blueprint where everything is connected and does the stuff what it's better designed for.
So yeah, just one more slide kind of on the planning. Here, in this slide, we're just kind of exposing some guidelines or some considerations that you can take around a number of the common operations you might run into in SQL DW. And so again, just some of the primary points I want to point out here. Focusing on the numbers, just focus on them relative to one another. Right? So these are workloads that we've either worked with customers on, been in the lab, and we come up with these kind of relative numbers, right? Again, for scan, a number of the loading functionalities, shuffle, and CTAS kind of operations. So what can I do with this? Well, one thing you can do is see, so again, let's look at the load heap, no partition. You can see kind of this fairly linear progression between DW 1000, DW 2000, DW 6000, right? So we've kind of done this basic testing for you. You can kind of see, again, some of the linear progressions there. But what this also kind of helps out with in terms of guidelines is a little bit around kind of some of these operations and sizing. So let's say you kind of you need to load 10 terabytes worth of data. So you can kind of see right from here, you go up to a DW 6000, then you can load around 7 terabytes of data. Again, if you're looking at kind of classic workloads, if you say, hey, what's my scan rate? This, by the way, happened to be from totally cold cache or no cache, remote storage. You can see, again, with the DW 2000, you're kind of approaching a scan of, say, 30 terabytes. And as an example, if you needed to troubleshoot, right, and you were seeing, again, some shuffle or some data operations across compute nodes in terms of troubleshooting, this kind of gives you some expectations on relative numbers that you'd expect to see, again, for these DW units. So with that, I'm just going to set the foundation around schema design. This may be somewhat fairly intuitive for those who are already on SQL DW, so I'll go through it relatively quickly. We're going to focus on just distribution, indexes, partitioning, and statistics. So table distribution options in SQL DW. Again, we have hash distributed, round robin, and replicated tables. Some of the main considerations, obviously on hash, the data is divided across nodes based on the hashing algorithm. The same value will always hash to the same distribution. It is single column only. It's not updatable. For round robin, that happens to be the default. You get the simplicity. It's an easy place to start, but at a cost, right? So in high concurrency situations, you're always going to have a lot of data movement there. Maybe great for if I just need to really ingest extremely large amounts of data really, really quickly, right? It can be optimal for that. And then replicated tables. Here, the data is repeated on every node. This can really help in simplifying query plans, reducing data movement, and it's best with joining with particular hash tables. There are some considerations. We'll talk about this in a slide or two, but you do have to be wary of updates to the replicated tables, and there is a limit in terms of the number of concurrent cache builds on the replicated tables to think about, which happens to be 2 today. It will also consume more space. I did put a star next to the hash distributed and the replicated tables because we did just announce either at Ignite or recently here at PASS that we have some Azure Advisor recommendations for these 2 options. So now in Azure Advisor, you can get recommendations around distribution and skew and whether a table might be benefit by being replicated. So having said that, quickly, some general guidelines on selecting a distribution method. Again, for large fact tables, the best choice is to hash distribute. You want to distribute on a column that's joined to other fact tables, primary or surrogate key. A number of considerations. Really the most important one is evaluating the query workload to assess the most common attributes being joined, right, which might make a good hash. So I think that's kind of really important. Of course, there are another number of other considerations, but really trying to understand your workload, that's where you're going to ultimately get the best benefit there. If no distribution columns make sense, I'd probably point ideally to potentially look at redesigning, right? So you can find a good hash distribution. Of course, as a last resort, you do have round robin. And just on the bottom here, there's a couple of commands that you can look at to evaluate skew. As I mentioned, the advisors also provide this information. I think from our practical sense as well, some skew is going to happen. In fact, one of the recent engagements I think we were on, they had almost 30% skew, but still met their SLAs. They had very, very strict and low latency SLAs. So again, some skew is not bad. You're going to have some data movement. For dimension tables, the recommendation for sizes under 2 gig on disk, you want to consider replicated tables. I mentioned some of the limitations on that. As well, if you scale, you'll have to rebuild the cache there. And for large dimensions, hashing is best. Just treat them like fact tables as well. So again, how do I avoid data movement? Data needs to be located in the same distribution. This is where you can really take advantage of those compute nodes and scaling out those compute resources, right, for performance. So again, you want to distribute on a column that's joined to other fact tables. Again, typically a primary or surrogate key. And as long as you have two distribution compatible tables that are joined, you can avoid data movement there. Similarly with aggregation compatible distributions. So optimizing with indexes. Again, clustered column store index is the default. And there are a ton of reasons to go with clustered column store index. As John kind of alluded to on Gen 2, we have the adaptive caching, which is taking those hot segments of column store from the remote storage, putting them in the NVMe cache, local cache for each of those compute nodes. So again, you only get that with if your table has the clustered column store index on it. Heaps are an optimal choice for temporary or staging tables, again, for very fast load performance. For non-clustered indexes, use them sparingly. I mean, there is some overhead in terms of data load, but certainly if you're doing small range scans or almost point lookups, then they can absolutely help out. Partitioning considerations. So if you look at partitioning in general, let's talk about some of the advantages. It really provides a great way to manage your data in granular chunks, right? So for scenarios like archival, it can be a great solution. It's just metadata operations and changes when you need to, say, switch in or switch out a particular partition. Certainly, if you have, for example, a daily load that's fairly large, and you can put that into a partition and then switch that in all at once, that can be quite efficient. And then re-indexing can also be done at the granularity of the partition, so that can be very helpful if you need to kind of rebuild indexes or remove fragmentation in your column store indexes. The one key point that I wanted to call out here is, as John mentioned earlier, you have these 60 distribution databases that come with however much compute you have in SQL DW. So typically, if you're thinking about, hey, I want a partition, I have this clustered column store index, you're looking to have something like 500,000 to 1 million rows in that clustered column store index. If you're doing loads of that much, 1 million, then ultimately you can get into the compressed column store segments. You don't end up in the Delta store. In DW, because I already have these 60 distributions, in essence, it's kind of partitioned for you. So what you really need to think about in this case is it's optimal to have 1 million rows loaded per distribution partition combination. So if you think about that, 60 times 1 million, you might want to look a lot more at, say, 60 million rows. Okay. So bottom line as well, it's just sometimes you already have some partitioning there. It's not necessarily that you have to partition. Optimizing with statistics. Again, this is another scenario where we do have the Azure advisors. It will tell you if your statistics are out of date and recommend updating them. The primary thing that I want to call out here for the people who are familiar with SQL Server, but not necessarily SQL DW, is create statistics are on by default, but there's not, all update statistics are manual. So you do want to think about updating statistics after incremental loads. Okay. And lastly, a couple of preload configuration considerations that we ran into with a few customers. Unlike SQL DB, TDE is not enabled by default. So if you do require TDE, please enable that, ideally before you're doing your data loads. The second one is choosing your collation carefully. So if you do choose the wrong collation, for the database level, you can only choose the collation at creation of the database time. So if you are moving from another environment that has different collations and you realize that much too late, then you may end up having to reload terabytes and terabytes worth of data. With that, let me pass it over to Alexei for some data loading considerations.
So before we start talking about data loading, because I'm honestly very excited about this subject. I do a lot data loading exercises with SQL data warehouse and without SQL data warehouse, and like process analysis, et cetera. And it's over the years became like very challenging and very exciting in terms like if, I don't know, 5-7 years ago, we were proud of telling like we can load terabyte of data. Now, I think we've got a decent amount of customers who are approaching petabytes of data range, right? And I'm just wondering, out of those who said they are already using SQL data warehouse, whose data warehouses are in range and under like terabyte? And like in the range in under 10? 100? More than 100? It's quite interesting distribution, pretty much equal. No, it's very cool because like data loading was always an exercise with a lot of variables, because when you start loading data, you usually start considering or asking yourself, how do you satisfy certain requirements, such as like, what scale of my data warehouse or database do I need to have in order to host all the data what I want to host, right? To run my queries and et cetera. Second, then you start asking yourself, how fast are my data sources? Can I load data quick enough? Because we are talking about terabytes range. It should be like relatively decent performance. And like how fast can you push into your I don't know, relational storage, the information. Then what often also a challenge is the transformation, because transformation requires compute. The more complex transformations you run, the slower you load, right? And then one of the classical, I would say, challenging questions was, am I designing my schema optimized for loading data, or am I designing my schema optimized for query performance? Because it's not the same. Like classical example, the heap table gets data insight faster than the table which has 25 and more indices created on that, right? So that becomes like finding the sweet spot and compromise where you still can satisfy performance of the queries, but you get the most of loading data. That's a challenging question. And there's tons and tons of details which can impact data loading performance, such as like what I call here schema efficiency, because we often see customers, it's not only customers, it's their IT departments, which say like, we don't know what the business unit will require for their analysis, so therefore if the data source gives me 500 columns, I would rather import all those 500 columns. But importing these white tables takes resources, so you cannot compare it to the performance of the slim, very nicely tailored fact table, right? also, if you never worked, some people here already have experience with data warehouse and they have some basic understanding like how fast their system can go. But if you're just starting that with data warehouse, then you would ask yourself, like, what's my minimal data warehouse scale to get the data fast? Like, should I start with 1,000 or go straight to 6,000? Right? And also, like, how fast is your data source? It might be different if you load from, let's say, Azure Blob compared to getting data straight from the Databricks. Depends on the connector and other things, right? So therefore, if generalizing, we're talking about two approaches. Like, one approach is when you either migrate your data from on-premise into cloud, or you need to like do backfilling operation, get your all historical data in newly created data warehouse. The key point here is not often, it's one-time operation. So you loaded all what you exported from your on-premise box, or you loaded all what you stored in whatever historical storage, right? And then you are sitting alone there. So there's nobody like business queries who you can collide with, you know. So therefore you can see how you, well, basically you can use all the capacity alone. You're monopolizing resource. You can get it the fastest way, which happens not often, right? One interesting part in which we had just recently, there are customers who need to restate their data warehouses. So basically, due to different changes like model or whatever, they would need from time to time to reload and restate the entire data warehouse. It doesn't happen every day. It may happen like, I don't know, once a year, once in a half year, but it's still like operation which wants to monopolize resources, and then you have flexibility of doing whatever you want to do in order to push data as fast as you can, right? And we're talking here about like the nearly full scale of the data warehouse, like it could be terabytes or tens of terabytes or whatever. Then alternatively, the other pattern is incremental data loading. And we know what the incremental data loading, the classical problem like late arriving data, where you get chunks of data which came like, I don't know, 1 week later, 1 day later, 1 hour later, or 1 month later. You cannot prognose it. Or it's just like natural stream of the data increments what you get, right? The key characteristics of this workload is it's tiny compared to like entire data warehouse restating. And second problem, this will collide, it is concurrency with your business queries. So this is where all this consideration about schema efficiency, like whether I optimize it for like initial loading or whether I need to pay attention to query performance, jump in, right? And we're talking here about way smaller scale, right? So it could be a couple of gigabytes. It could be also terabytes. We see customers who are like daily ingesting like several terabytes of data, but still it's a small percentage compared to the entire data warehouse side. Couple of words about migrations, because migration is one of the typical scenarios, because we see customers either starting from scratch, like building data warehouse for new applications, for new workload from scratch, and other scenario is where they say, I want to migrate due to cost reasons, due to like modernization reasons or motivations. I want to move my data in Azure Data Warehouse, right? So what are important, it is like a decision tree here. First of all, you need to get your data out of your current system. It could be a current data warehouse. It could be current like SAP system or whatever. So you need to extract data, and usually what people do, they extract it in form of CSV, of TXT format. So what you really need to think about here, you need to find the moment where a system is not loaded, and you need to have quite performance storage in order to absorb all the data what you're extracting. Second is, once the data extracted, you probably would want to move it in some like cloud storage, like Azure Blob Storage, for example, right? So what you need to make sure then, what your network pipe can push the data as fast as possible. So a couple of solutions here, for example, optimally would be have something like express route, which can push data nearly with the performance of your local network speed, right? And then often what we also recommend is, because you need to, you may benefit from parallelism here. So chunk your data files chunk your information in a number of files and leverage parallelism of pushing data over the wire. We had like back a couple of years ago a customer who migrated entire data warehouse, which was about petabyte in size, right? We were looking at different options. We figured out like basically creating a number of virtual machines with easy copy and using express route. Online, we managed to load all petabyte within like 10, 12 days. Where if we had chosen different option, like writing it to the drives, shipping it over to the data centers, alone like copying data to the USB drives would take about like half of this time, plus shipping, plus extraction and blah. So overall, the prognosis was around about 20 days. So depends on like your size, your situation, but sometimes using transfer over the wire might be very efficient. And then it also depends which tools you're using. Like as I mentioned already, easy copy is a great tool for files move. That's like one of the best options. You can also automate the data move, like you can implement orchestration using Azure Data Factory, have runtime installed in your environment, and rely on Azure Data Factory to move your data. Like you need to play with all those options and figure out what's your best, like what tool suits you the best. Now, about data loading options in the data warehouse, I would start with Polybase and say, from what we saw so far, Polybase probably is the best option. It's the fastest option what we have today. And Polybase is integrated in multiple different tools. Like a lot of people probably use SSIS, right? So if you're familiar with SSIS, SSIS has native Polybase connector. Then very famous alternative to Polybase, Informatica, also natively supports that. And some internal operations of SQL data warehouse, such as a CTAS operation, they rely on the Polybase for transferring data. However, not everyone has this freedom and flexibility leveraging Polybase. Often people would need to deal with commodity tools or applications which rely on BCP or SQL bulk copy. So the Polybase leverages internal compute and in order to push the data, where BCP or SQL bulk API based tools, they will go through the control node, right? And they will actually digest the amount of network connections what you have on the control node. You can still use bulk copy API and parallelize your workload, but you'll be consuming the network connection capacity what you have on the control node. So therefore, it is an option. You can also get great results there, but it's way easier to push the data with using Polybase. Now, talking about Polybase characteristics, it's the great thing about Polybase, it automatically parallelizes data workload across compute nodes. So the more compute node you have, the more active readers you have in your configuration. Polybase even does a great thing. If you have a large file, it will initiate multiple processes reading out of this large file, which is great. So you don't need to pay attention anymore to like how many threads do I need and blah. So you rely on Polybase on this. So Polybase depends because of that on the stuff what the guys already mentioned, resource class. So resource class basically how much memory you get per like kind of container, right? It also depends on how many data warehouse units you have. And also we'll talk about that what type of file format you're using. Now, there's one gotcha here, what we've got, or not what we've got, it's like known fact, right? If you use compressed files, gzips, you'll have only one thread per file. So compared to like Parquet or to TXT files where you have multiple threads per file, gzip has one file. Therefore, if you need to deal with compressed file formats, make sure that you initiate multiple data ingestion streams, right? So basically manually force, like for example, put multiple gzip files in the same folder, and they will be read in parallel, so you still get a relatively good performance. Now, when talking about data loading, I want to spend a couple of minutes talking about readers and writers. Who are familiar with this concept? OK, there's a good amount of people who know that. For those, sorry, I'll need to repeat this for those who don't know. Right? Basically, when Polybase initiates data loading process, it generates threads for reading operations, and it generates threads for writing operation, right? And as we discussed, like this depends on how many data warehouse units you have. So basically, the more data warehouse units you have, the more read operations you will initiate. You can, I'll talk about that a little later. You even can see using some DMVs how many active read operations going on your cluster. The read operations, amount of read operation depends on the file format. And as you see on the table, the most of the readers will be initiated for the Parquet file. Now, classical question, which I heard a lot when we were talking about Hadoop implementations. It's also relevant now for SQL data warehouse. What is the like best size for the files which you ingest into your data warehouse? And the answer is 512 megabytes chunk, right? So make sure that your files are equal or bigger than 512 megabytes chunks. Otherwise, you run basically, think about that as a operation, right? And if your file is smaller, you still initiate this large chunk of information. You basically spend capacities for nothing. So try to make sure your file's bigger, equal or bigger than this size. Now, for writers, it's kind of similar. So writers scale with amount of data warehouse units. What we saw here is also that scaling after certain amount of resource units doesn't bring necessarily too much of the scale. Like you see here on the table, if talking about static resource classes, we see significant improvement moving from, what is this,
30 to 40.
From 30 to 40, right? You nearly double your throughput. But then moving to 50 and higher, actually, it doesn't give you that jump. So if you ask yourself, like, what resource class to start with, the rule of thumb, look at 40. And then when you run your workload, you can execute the procedure, the DMV, what we're showing here, and then you can see what a realistic number of writers or readers you have on the system. So it's very easy to monitor. And like playing with this number, you'll find your sweet spot here. So the recommendation, depending on solution, like if you talk about, let's say, initial data loading, try to use the highest resource class, what gives you best performance, right? And if you use static resource classes, you can actually benefit from concurrency because you can balance between amount of resources which will be utilized by data ingestion process, as well as there will be some resources left for querying and et cetera. Then there is a procedure which you can run to.
Let me just comment on the procedure. So there's a procedure. Right now it's for Gen 1, so we're looking to get the one for Gen 2 out. It will make recommendations based on metadata on your table on the best resource class to run under. So again, looking at the readers and writers is very important, as we kind of showed with that static 30, static 40, et cetera. We do also have some guidance We point to a blog that the CAT team wrote that shows a number of the readers and writers. So again, you can validate it here. And then this new update on this PRC workload management by DWU can also give you hints in terms of the best resource class to run under.
Yeah. Let's spend a couple of seconds then talking about Polybase. What we see often, SQL data warehouse gets surrounded by like no SQL type of solution, like there's just the data which were processed by Spark or some other systems generate data and pretty much common in that space Parquet format. As if you remember the table I showed, the amount of readers and writers for Parquet was like the best combination, so you basically can read it faster than any other format like TXT or C. That's one. Second, people like it because of OSS community support. People like it because Parquet has schema. It's compressed format. So there's a lot of great stuff there. But there is also a couple of pitfalls. Parquet has its own formats. Like my favorite one is the datetime format, which does not necessarily meet the datetime definition of the SQL server. And if you want to have a lot of fun, you can try to import straight datetime from Parquet data type datetime from Parquet into data type SQL, right? And you'll have a lot of fun, guaranteed, right? So if you have no time, and unfortunately we had a couple of situations where we had to work with customers and push data as fast as possible, the recommendation there was like what we came with, take string and import datetime as varchar code, and then you can extract this and transform into SQL native datetime by using CTAS operation with cast, for example, or something. So recommendation here, if you have time and you want to play with this, and there's a bunch of other, that's why I put the table on the left here, bunch of other formats which don't necessarily match, even though the names are similar to the SQL data types. So if you get stuck, import as string and then do cast in data warehouse locally. Then, as we mentioned already, the read-write balance is the best, right? And then there is one little problem. What we figured out it might become a problem. As I mentioned earlier, a lot of customers they have like extremely wide tables and they want to import this extremely wide tables. Like NoSQL solution might not have issues with this, right? Deal very nicely with 500 and more columns. The problem is if you specify external table on top of such structure, we cannot filter out columns we don't need. So therefore, you have two situations here. Either you will not be able to import it at all, right? Or you, if you're lucky, you could then play with like other workarounds, right? But the key message here, if you see some very wide tables, always ask yourself whether that's what the business needs, because it's not only a problem what the Parquet has, but it's also the thing related to processing of these wide tables and then running queries on top of them is not probably the most optimal thing for data warehouse to do. Now, so coming back to the patterns, we talked about historical data load or restate and these kind of situations where you are alone on the data warehouse. So the recommendations here would be, and that's what we did for a number of customers as well, like if you have those situations or cycles where you need to massively load data, go scale it up, load data fast inside, and then scale it down, and then let the queries run, like reporting queries and others. So not only data warehouse units amount, but also resource class in this situation might be used the highest possible. A couple of interesting observations is CTAS operation is the best one. right? So CTAS is minimally locked operation. That's what allows you to push data from your external table, for example, into destination table. Couple of things I learned myself from John is what you may specify, which is by default is not there, but you may specify using local tempdb in order to accelerate data loading. Because if you remember the architecture of SQL data warehouse, right, we persist data or persisted tables stored in the blob, whereas temp table, they all reside on the local SSDs. So therefore, if you need to do something like load data from external data source, do some operations and load it then in the persisted storage, those transformations like staging area, right, may be done through the temp table. You need to pay attention though, like if some service disruption happens, you need to retry this operation, but that might be something like you can sacrifice based on the performance advantages what you get from the system. Then incremental load, there are situations where you cannot do CTAS simply, right? So you need to load a couple of rows or a couple of million rows, and they are so sparse, like they separated across multiple partitions or whatsoever, right? So you cannot use batch, quote unquote, operation. So you need to stream it directly in your table. You can, the benefit here, if you need to do this, or if you have to do insert into, you are not sacrificing concurrency. You still can query your data warehouse from like reporting queries and others, but the operation is fully locked, therefore it's not giving you the top performance. So alternatively, like what you can do is imagine you got like incremental daily load. What you can do, you can load this into heap table, then create all the indices, and if your table is partitioned, you can do switch operation, right? So you get then data in no time available for your querying. The problem here is that switch operation, so all will run relatively quickly, unless you need to do the switch operation. Switch operation requires the entire table metadata lock, right? And if there are heavy queries running on the table, you may wait forever, right? So therefore, it has like pros and cons. It's minimally locked, but the schema lock release may take time to wait for. So maybe, like I already mentioned, insert select is good, but prefer CTAS if possible. Talking of the white tables, there is also another reason here. Like if you use Polybase to import data, there's a 1 megabyte limit per row width. Therefore, that's another motivation for you to consider using slimmer tables if possible. Then white tables have significant performance on ingesting that, but also on the query performance. Like when you query white tables, it might become a problem not only for loading, but how fast your queries run. And in general, we have a number of best practices published in Azure Data Warehouse loading and strategies. Also, I would recommend pay attention to the blog what John runs, because he talks about some of these patterns there as well. And I think with that, we like naturally come into the point where you loaded data, you're all happy now, you want to query it.
So I'm going to talk about query performance tuning. I guess my first question for you guys is that what has been your experience in performance tuning in data warehouse, and specifically reading the DSQL plan? Any feedback? Is it easier like SQL Server, or is it intuitive reading the explain XML, or any?
It's a leading question.
Okay, so hopefully I can help you a little bit, right? So what happened is, the first thing is obviously that performance tuning on SQL Data Warehouse requires actually several layers. From the SQL plan is that there's going to be 2 layers the distributed plan, and then the SQL Server plan, right? So first thing, the SQL plan is basically the way that it works is that it breaks up a complex queries into multiple steps, and using the so-called secret sauce to solve the data. And some of it requires data movement, and other is just basically trying to break up a complex query. So the way that you get the SQL plan right now is that again, you can get an estimate plan by using explain. So put an explain before your queries, and then just run the queries within, say, SSMS, and then you get an XML plan. I'll step through how to read the XML plan a bit later after this. But for now, that's the way to get one of the way to get executed plan. It's actually the most detailed information that you can get. It's the only plan that you're able to get if you have a shuffle move operation and you want to find out what particular column it uses to do those shuffle move operation. That is the only way for you to get that information. Okay. Next is that recently we released the GUI plan, which is within SSMS. You click on that icon, and it displays the estimate plan for you, right? It's GUI, nice and neat and everything. And I would recommend that would be the first thing you do because it's cheap, because it doesn't cost you anything, but you get a high level of what the plan is doing. And then obviously the actual plan, the only way for you to get actual plan is run the queries, and then you would capture it with the exec request to get the plan. So some of the fundamental steps is obviously, with the SQL plan, you get 3 major operations. The first one is on operations, which is running the SQL Server queries, and it's basically mainly on either the control node or the compute nodes. And then, of course, the DMS operation, which is the data movement operation we talked about, the shuffle move, the broadcast move, the partition move, the trim move, and so on. And then the return operation. So after, this is usually the last step of the query plan in which all the data is being compatible, joined, and then I would go and get the results that I either stream the data directly back, or I still need to go against SQL Server to solve the join and then get the data back from me, right? And sometimes, a lot of time that, that SQL Server could be the bottleneck during the return operation. So again, each step, run a SQL plan from all this. So from looking at the SQL plan is that you want to see, obviously, what the steps are doing, right? You want to get an idea of, is it doing the right thing? So, and then also, with the MPP, you want to drill down, and you want to see that at the node level, is it processing all the data, or are there any skew? Is it, when it's moving the data, is it reading from a single source, or single node only, or is it writing to a single node only? So the reading and the writing can be skew. So that could be, with the MPP, skew is actually, your deadliest, weapon, enemy, because there's no point in having an MPP if you have a single node doing all the work, right? So something that you want to check for is that, look like a table, right? Do I have my statistics? Is it updated? How can I find out that, why is it thinking that it's doing a broadcast move when it should be doing a shuffle move, right? A distribution, am I compatible? Am I hashing on the right key? And should I be using replicated instead of round robin? And again, how many rows am I moving? Am I moving 10 billion rows? Or is it applying the predicate appropriately, where it's only moving only the data and the column and the row that it needs? And then, of course, some people, we have this concept of you can query data on storage, and we call it an external table. It's not really practical, right? Because what happens is that the way SQL Data Warehouse solve it is that I start bringing all the data back into the engine via the Q tables, and then it applies the predicate. So even when you do where select star from external table B, where date within 90 days or something like that, it's not going to only pull in 90 days. It's going to pull in all your 1 terabyte, 10 terabyte data back into the warehouse. So it's not practical. If you need to load the data, it's faster if you load the data and then query against it, okay? And then views. A lot of time when you do a select star against view, people think, oh, it's just a select star. No, it's not, right? we can see some very, very complex join within the views. So one of the things you want to make sure is that you solve the compatibility. Make sure that view is not compatible with join. If not, then underneath, from your user query that you may not see, the views can have a lot of these SQL steps that actually has to solve that. So some of the DMV that's useful is obviously you want to start with sessions. How many people are running stuff out there, active session, and so on. And then next is that you want to see the exact request, right? What queries how many queries are running out there? What's the status of my queries? And then you want to look at the query step. So the request step is where you want to see the DSQL step. So that's from the high level what the DSQL step look like. And then if you want to, if there's no DMS operation, the SQL step would give you information about what particular query is running on the SQL level. And then, of course, if there is a DMS operation, you want to take a look at the DMS workers. And this is where you can drill down and you click at the reader step, all 60 of them. You want to look at the writer step, all 60 of them, to see, again, if there is any skew, if there's any one node is slowing, or there's a bad node. So those are the steps that you want to take a look at, right? And of course, the weights. So this weight right now, as you know, that is only revealed the locks and it's only revealed concurrency. It doesn't give you the typical, IOs or CPU or anything along that line. At this time, we're only exposing that. And again, and then within the DSQL, you can use the DBCC PDW show execution plan, and that would gives you the SQL Server estimated plan within that particular node that you're running, okay? And then, again, the performance tuning is, what is the system doing? And then is it, the small number of long-running queries running? Making sure that you want to see, all the CPU and the resources. And, and then if I have high number of quick-running queries, for example, how are they contending? Are they exceed the concurrency? And what resource class are they running against? So, and then there's also some contention, obviously, with load impacting the queries running out there. Okay, so here's the query life cycle. So the reason I want to go through all this is a lot of the time it's even before your queries run, you may have some bottleneck. So the pattern is that you submit the queries, it goes through a parsing, and then it's go through the memo gen, generate the plan, and then it gets checked to see if there's anything object lock, and then system lock and execution. But if you take a look between the submit time and start time, if I have any concurrency slot, for example, I could be sitting out there, and the time that could be during that time that the queries are actually being queued, it's not running at all. There's other cases that I have a generated queries from third-party tool that could be 500 to 1,000 lines long. And the data warehouse sometimes can take, from what we saw, 30 seconds up to 58 seconds to generate a plan, right? Because it's so complex, it's 1,000 line long. So those are things you want to watch out for, even before your query is executed, to see if is it within before the query is being submitted. Okay. And then again, so the typical common data movement operation is shuffle move, which is basically redistribute all the data, specifically about the fact table, to make sure I have a compatible join. Partition move is basically I aggregate the data, get to the control node. That's the final aggregation. And the broadcast move, which is basically making the table replicated. It's more efficient that way. And I have an example of a query here. And I guess the first step is, so here I have, if you guys are familiar with TPCH, the line item table, order table, and then the customer. This query is basically get a summary of the data from the 3 table with some predicates and do the group by. So it's a top order ranking type of queries, right? So what the query, if you look, the way you look in here is that this is kind of neat to look at because you know that offhand, this is solving the customer queries because he's been hashed on customer key. Customer is being joined to line item by the customer key, but it's cheaper for it to do a broadcast move on the customer, make it a replicated table So line item, instead of moving all the line item table on the customer key to join. So by doing the broadcast move, it's way cheaper to move this small dimension table versus the moving the whole line item table. So it does a broadcast move, and then this is the order table, and it's it's basically applied the predicate here, and then does a join against the customer. And here's the line item table. Again, it's apply the predicate, and then the order and line item would join, does the aggregate, and then gets the result back. So nice and neat. The other way that you can look is this is the actual plan that we talk about, right? So this is what it's actually looking like right here when you run it. So here again, the on operation. So this is first thing it does create the temporary table. It does a broadcast move, and here's the SQL statement that it's generated, and the return operation. This is what we talk about. Once it has the comparable join, it goes through the return operation, and then at the end of it, it's dropped the table. So this is what you would typically see with a DMV query plan. Finally, this is, again, we talk about this is probably the most complex one because it does have a lot of information. So what you can see here is that what your current DWs are. Here's the query text, right? And then here's the total cost for the plan and the number of operation. So you typically want to use this information right here, especially the total number of operation. Total cost is sort of like arbitrary number. You can't really make anything out of it, really. It's just because the cost is higher. In this case, that doesn't necessarily mean it's more expensive, but you definitely want to take a look at this to see when you make any changes to the schema, statistics, what did this look like? So that's what you want to look at first. And then next is that stepping through, first we would create the temporary table to prepare for the broadcast move. And here's the broadcast move right here. It's estimating that I'm going to have this amount of rows, and then this is the particular query that's solving. So it's moving the customer key and making a replicated table and apply the predicate right here. This is what you want to see, right? One of the things you want to see is that when it does the data movement, make sure that it's just moving the column only and the row that it needs only. There might be some cases that you have very, very complex queries that the plan may not do that. And in those cases, you may have to rewrite the queries to enforce that. One of the things that we have here is that it's actually preparing for you, but basically this is what getting us ready for query startability. So what that means is that in each one of the steps is have a save point. So if there's a service disruption, if there's a node failure, the queries would actually restart automatically for the end user. From the end user standpoint is that he submitted queries, failover happens, and the next thing you know is that the query might take a little bit longer because the failover taking place, and the query will get restart, and then the result would come back. Versus in the past, he has to resubmit the queries manually, right? So that's a pretty good thing to do. And then, so the best of it is that again, once it's going to have all the comparable join, it just submit this query. This is the core query that would run on the SQL Server compute node and get the information, okay? And this is just the rest of it. So summary is that you want to make sure that you check for SKU, use BSPC shows space use, and then make sure your statistics is up to date, and then the minimal is that you want to make sure you have statistics on the join, the group by, where, and then the distinct. The other thing that because of the adaptive cache that we talk about, right? Go out to the portal, check for this cache hit ratio, right? So if you have a high cache hit ratio, you're doing something good. If you don't, then you might have to warm up the cache or do what you need to do to get this number high because, or else you're not leveraging the caching, right? And then the other thing is that make sure your replicate table is being built because and when you do any DML operation, when you update statistics, it's actually validate that replicate table cache. So therefore, you want to make sure that it's updated. And then, CTAS the table for return operation, large return operation. The client's kind of slow. If you're going to return back 10 billion rows, for example, it's better for you to CTAS doing a table or doing data export into blob and then get that information to your end user versus waiting for SSMS or any client to return a large resource operation. And then sometimes, it's better for you to denormalize the data, the schema versus having complex join, especially if it's not compatible, right? The SQL step, I think this is pretty much, we talk about, we're kind of short on time, but bottom line is that make sure your predicate push down we talk about, use the high resource classes for your high memory usage, and then use the poly-based export. Materialize the table if you need to. We ran out of time?
Yeah, so we just have a few more slides. If you wait a couple more minutes.
Okay, yeah.
If you're interested.
Yeah. So we're going to talk quickly about analysis services, right? So again, the recommendation is use analysis services when you're looking for cache with high concurrency performance you're looking for. Again, SLA is 3 seconds. And then the architecture design point is that you want to make sure you have the right size, right? Typically that you have an enterprise customer that say that, well, I have a large amount of data. I don't really know what my usage does. But it won't work that way, right? Because there's also a limit right now, 400 gig, with the largest SKU of S9. Sure, you can go with VM. With the M128, it has 800 gig, but it can be expensive, right? And then there's also manageability behind it. And the point of it is that avoid a one-size-fits-all cube. You always want to sort of like design a cube specific for a certain user. Keep it small because the complaint here is the latency of processing the data into analysis services, right? When you talk about processing terabytes of data, it could take days. So, and then optimization is obviously using parallelism as much as you can. Data warehouse, you can scale out. You can have all this reader and writer. It's scanned really quick. The problem is that on the analysis service side, you want to make sure that you leverages all this max parallelism configuration, so it increases until the bottleneck. And typically, what we're seeing the bottleneck is during the vertipack. So when the data is ingress into the analysis services, the process of compressing the data into the vertipack is actually a single threaded. So that is the bottleneck that we're seeing right now with processing for analysis services, right? And then again, make sure that you get the right resources when you process it. Again, if you want to get as quick as you can, use a static 80 or X large resource class, but during an incremental processing or something like that, it's maybe you want to use static 40 and then allocate those other resources for the people running the queries, data loading, and so on, right? We talk about balancing the concurrent slot use, versus the performance gain to make sure that everybody have their piece of the pie, basically. The other thing that we notice is that avoid using view with complex joint because, again, views, it has to go and solve that problem. So better for you to materialize that, pay the price up front within the warehouse. So materialize that, CTAS it, make it, and then when you do a select star against that, the processing will be way quicker. The other thing is that very, very wide table. How wide? Hundreds of columns, right? Because people can be legacy system. They just basically put everything on there. They didn't have to worry about all this, having a no more, optimized schema. But an example that we saw is that the 3 column, for example, when we have 12 parallel threads on the M128, with all this core information like that, and we're only looking at getting 50 megs per second, right? And if we reduces that, it's actually, we got 3 times better, faster performance if we reduce the column. The point is that get the data to AS, only the data that you need and the column you need. Don't try to put everything out there or else you're going to pay the price. Okay? So key takeaways, obviously, the end-to-end architecture always depends on your workload. You have to understand your workload, right? Do I need the Spark layer? Do I need the Databricks layer? How about some Event Hub? Do I need AS? And so on. Schema design is critical. You really need to spend time to understand the query pattern so that you can design the distribution, the partitioning, making sure you have the right row counts. Polybase, obviously, is the bar none, right? You have to use Polybase. It's the quickest way to go. I remember the gentleman earlier says, one of the reasons why you want to go data warehouse, again, the compute power of the ingestion. Data warehouse can give you terabytes of data per hour. Whereas if you go SQL DB, for example, you have that log limitation, 40, 50 megs per second, right? So how fast you want to ingest the data, how much of the data. It's all about the scale-out compute power that you need. Data loading performance, depends on DW, the resource classes, the file compression. Update statistics is very optimal. It's very critical for your performance, actually. And then, larger resource classes more or less for the memory, and then the readers and writers associated with that. If you need, it's not going to help you if you require compute power. For compute power, you need to increase the DWU, okay? And then leverage is the multi-tier caching, right? Design, make everything cluster column store. That's the column store, cluster column store leverages the caching. If it's heap, if it's anything high SCCI, it won't leverage the adaptive caching. Warm up, if after incremental data load or nightly update, for example, you might want to profile the queries and maybe warm up those queries, similar to what you do with analysis services rollout, right? Warm it up before the user comes in the morning. So that may help them, because or else, the first read is going to pay the price by reading the remote storage. Only subsequent reading and leverage the caching. And then, of course, monitor. Again, we talk about the cache hit. And then performance tuning, basically at the resource level. So take a look at, we release this, CPU, we don't have memory yet, but we will, and I/O, counters out there on the portals. So leverage that. Take a look and see what the system is doing first, right? Next is at the SQL plan. You can tune at SQL plan level and then the SQL Server level. And then, again, use analysis surface of low latency, high concurrency dashboard queries. Usually Power BI directly on top of a warehouse is likely won't work. It will work in limited scenario, but when you talk about ad hoc query dragging and dropping terabytes of data, it will not work, right? It will be very slow. Okay. And finally, optimize data transfer to AS by taking leveragism, parallelism, and then resource classes, get in the right resource classes, materialize the complex joins, and then process only the columns and the data that you need. Okay? That's it.
So really appreciate you everybody here for coming and staying a little bit late. If you have questions, we're happy to stick around.
Yeah.
I think the next slide is on.
No, I think that's it.
Yeah, please give feedback and evaluations.